Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
The research mathematician is searching for something never before seen. More often than not, that thing is a published paper which contains no discovery and contains no invention that benefits humankind. In academia, a published paper is rewarded. A mathematical discovery that benefits humankind is 1 million times rarer and is not rewarded in proportion to the effort required to discover it. For this reason, the research mathematician in academia only asks questions that are important to his career. The research mathematician asks questions that are direct and centered on abstract mathematics, not questions that are central on extreme-scaled parallel processed solutions of the real-world problems arising in mathematical physics. In the second half of the 1970s, I was a research mathematician amongst research physicists and research supercomputer scientists. In the first half of the 1980s, I was a physicist amongst mathematicians and supercomputer scientists. In the second half of the 1980s, I came of age as an extreme-scaled parallel processing supercomputer scientist that was amongst computational physicists and computational mathematicians. That 16-year-long quest was the reason my experimental discovery of parallel processing made the news headlines in various industry publications. Looking back to the 1970s and 80s, I knew there were no easy partial differential equations waiting for me to invent them. It is rare for a mathematician to invent a never-before-seen partial differential equation. It is rarer for that equation to make the news headlines. In the cover story of the May 1990 issue of the Mathematicians newspaper called the Siam News, I said that I invented 36 partial derivative terms of calculus. I also said that I invented 36 algebraic terms that corresponded to those 36 partial derivative terms. Those 36 partial derivative terms represented the temporal and convective inertial forces that impact moves crude oil, injected water, and natural gas and moves them from water injection wells towards oil and gas production wells. Those 36 partial derivative terms that I invented can be used to correct the critical errors in the mathematical techniques that were used to discover and recover otherwise elusive crude oil and natural gas, namely the governing system of partial differential equations of calculus. If uncorrected, those 36 errors will replicate themselves across the trillions upon trillions of the system of equations of algebra that were derived from discretizing the governing system of partial differential equations that were at the mathematical core of the petroleum reservoir simulators that I used to discover and recover crude oil and natural gas. My contribution to mathematics was to install those patches of 36 partial derivative terms and to add them to the pre-existing 45 partial derivative terms. Those 36 errors occurs at 3 levels or as errors in the partial differential equations that in turn become errors in the system of partial difference equations that were derived from the discretized partial differential equations. They also become errors in the supercomputer algorithms that must be executed across millions upon millions of processors. The new calculus and new algebra that I contributed to mathematical knowledge was extremely difficult to invent. In parallel processed computational mathematics, ranging from petroleum reservoir simulation to general circulation modeling of global warming, the trillions upon trillions of x's and y's of the underlying extreme scale algebra had their origin from the partial differential equations of calculus that in turn originated from and encoded corresponding laws of physics. A mathematical analysis is akin to substituting thoughts and prayers for experiments across millions upon millions of processors. On the 4th of July, 1989, in Los Alamos, New Mexico, United States, and 15 years after I began supercomputing in Corvallis, Oregon, United States, I experimentally discovered that the toughest real-world problems arising in computational physics could be solved across a new supercomputer that is configured as 65,536 processors that tightly encircled a globe and encircled that globe as a new internet and encircled that globe in the manner the internet encircles a bigger globe, namely planet Earth.
Insightful and brilliant lecture.